I am Chak Murr. I created Forth 45 years ago. It is still being used, which is moderately amazing. It's certainly being used by me. It's the only language I would ever consider programming a computer in. I am the CTO of a company called Green Arrays, which is a startup that's been in business about 5 years, so it's not exactly a startup, but we're still looking for customers, a killer app, investors. We have a high-speed, low-power multi-core chip, 144 computers on a 5mm chip. It's a remarkable little chip. It's a lot of fun to program. It has enormous computing capability. I'll show you that in the next slide. So first I'm going to talk about Forth, and then I'm going to talk about the Forth engine, which is a computer which runs Forth very efficiently. Show you some Forth programming, and then point out how you can program in low energy. And I recommend that all of you keep energy in your mind when you're writing programs, because PCs are going to be going away. Smartphones are going to be embedded. Embedded meaning embedded in your body, in your ear, in your eye, in your heart. And power is going to be crucial in those applications. If we talk about smart dust, where you have untold trillions of computers floating in the air, they aren't going to have very much memory, they aren't going to have very much power. If you talk about molecular computers that are circulating in your bloodstream, they aren't going to have much power, they aren't going to have much memory. And they aren't going to be able to use much energy. So keep that in mind as you move through the next 10 years. Let's go to the next slide. All right, here's 144 computers, just so that we know what we're talking about. There are 8 rows of 18 computers. And in the geometry of a chip, that turns out to be square. Each computer can talk to its neighbors. It's a mesh of computers. Yeah.
Neighbors, 4 neighbors, 8 neighbors?
4 neighbors. Each computer takes 1.5 nanoseconds to execute an instruction. That means it's running at 666 Mips. It takes 4 milliwatts if it's running flat out, which is 7 picojoules per instruction, which is small. Now, I'm going to be talking about energy. There's energy and there's power. Power is energy per unit time. Power is watts, and a watt is a joule per second. So it really doesn't matter how long it takes to perform an operation. An operation is going to require a certain amount of energy. It requires energy because you have to charge capacitances, and you have to run currents through resistors. But energy is the key. And one of our instructions takes roughly 7 picojoules, more or less. One of these computers takes 100 nanowatts if it's idle. Remember, there's milliwatts and microwatts and nanowatts. So it takes very little energy just sitting there. And with 144 computers, they all power up idle. So the chip at reset is drawing no power. The entire chip can run 96 GIPs, 96,000 Mips, which is a lot of PCs. It only takes 550 milliwatts to do that. That's half a watt. If the chip is idle at reset, 15 microwatts of leakage current All the transistors are sitting there, no transistors changing state, but you still get a little bit of leakage through the gate. This is what I mean by low power. This is the lowest power computer that I know of. Green Arrays, one of Green Array's customers developed a chart showing all existing computers, commercial and experimental, and we're right at the top of the list. This is about the best you can do. The only people that can do better are those that deal with sub-threshold logic, with high noise margins, and this is a good computer. The computers are numbered from 0 with their row in the column, 0 to 717, and I'll be referring to those numbers. So that is my motivation for talking about these things. I wasn't paying any attention to energy until a couple years ago when we started realizing that this chip is remarkably low energy. And now that we know how important it is, I can reduce the amount of energy it's using, and I will be doing that. I've been to a number of hardware conferences where people are talking about designing ASICs, large ASICs with millions and millions of transistors. And I always considered that size and speed were important parameters. But in the modern context, there's only 3 parameters that matter: power, power, and power. You've got to reduce the power for portable applications and also to reduce the energy used by these server farms that require a nuclear power station to run. Okay, here's one of the computers. It has 18-bit words for not very important reasons, but it's a very happy number. It lets you count up to 256,000. It has a 64-word RAM. That's not kilowords, that's words. You can pack 4 instructions per word, so each computer can execute up to 256 instructions. That's what I mean by saying it's a small computer. And that has implications in the way you program it. As characteristic of fourth computers, it has 2 pushdown stacks. One which is common to all computers, and that is a stack on which you store return addresses for nesting subroutine calls. The other, which is pretty much unique to fourth, is that you store parameters on it. Anything you read goes onto the stack. Anything you write comes off of the stack. There are 3 registers that are interesting there. T is the top of the stack, S is the second element in the stack, and R is the top element on the return stack. The programmer has got to be aware of these 2 stacks and manipulate them nicely. Nothing is done automatically. There are 3 address registers. P is the program counter, which is where you are in the instruction stream. A and B are just registers. There are 4 communication ports to your neighbors: up, down, right, and left. And you can read and write to your neighbors. You can read and write to all 4 of them if you want to. There's a bit for each port in the address. So that is the context. Those are the facilities available to a programmer. Here is the instruction set. There are 5-bit instructions. We can pack 4 per word, except that in the 3rd slot, you have to add a couple zeros. So in the list of instructions, those in red can be put in slot 3, and all the others can be put in any slot. Jump instructions can be in either slot 0, 1, or 2, and all the remaining bits in the word are the address for the jump. I'll just briefly go through the instructions. This is a perfectly conventional instruction set, except for a few in the right-hand column. You've got jump, you've got call, you've got jump if 0, you've got to jump if positive, you've got to jump if the R register is non-zero, and decrement. So that's a decrementing count for next loop. In the second column, you've got fetches and stores. Fetch from register A, fetch from the address in register B, or fetch in line in the next word in the instruction stream. And the same equivalent stores. Third column are ALU operations. You've got binary operation, add, and or. Unary operations, 2*, 2/, and minus. The binary operations take as input the contents of T and S, the two things on the top of the data stack. And they return an argument in T, throwing away S. So it's a stack operation. These are called zero operand instructions. The only reason I can pack them into 5 bits is that you don't have to specify their operand. The operands are known. In the third column, you've got some stack operations. You can duplicate the top of the stack, you can drop the top of the stack, you can pop the stack from S from the return stack into the data stack. Vice versa, you can push the data stack onto the return stack. And then 3 interesting instructions. So you can store into register A, store into register B, read back from register A, and do nothing. The dot is a no-op. No-op is essential in order to fill in slots in a word, instruction word that you haven't used. 32 instructions. If you haven't memorized them already, it would only take you another 5 minutes. And that's partly what I mean by saying this is an easy computer to program. Now, if you're familiar at all with Forth, those are Forth words. There's a one-to-one mapping between your source code and your machine language. The compiler is a few dozen lines of code. It doesn't optimize, it merely translates your source into the machine language. This is a different world from what I've been hearing in the last couple days. It may be a world that dates back to 1968 and is not interesting to you. But again, I caution that the future is going to be different than the present. And I'm happy to deal with a very transparent, very small compiler. We can argue about whether you call it a compiler or an assembler, because it really doesn't do anything. But compiler is a more impressive word. Here's the code. Here's code for one of these computers. And this is an example of color Forth. I created Forth in about 1970, and I've used it ever since. I call that classic Forth. Color Forth I devised in 2000. It has a number of nice features, mostly that I felt I needed a new language for the 21st century. But one of the things it does is it reduces the amount of punctuation. Forth has very little punctuation compared to, say, C. But color Forth has almost no punctuation. Instead, it uses color. Each source word in the source code, each word in the source code has a tag that indicates its function. And the function is reflected in this editor as color. White words are comments. They're ignored. Red words are being defined. So the definition of go is the green words that follow it. Those green words are compiled. The yellow words are executed at compile time. They're direct commands to the compiler or to the compiler. The gray words you see there are inserted by the compiler to tell you where you are in your 64 words. When we finish the definition of go, we've used one word of memory, and so your program counter is set at 01 in hex. Init marks the end of code which is compiled into memory and begins the code that is compiled, that is executed at load time. These computers have got 4 ports, and you can read and write to the ports. They're memory mapped, so you can also jump to them. If you jump to a port, you are waiting for your neighbor to give you an instruction. If you jump to all 4 ports at the same time, you're waiting for one of your neighbors to give you an instruction to execute. And it is the programmer's responsibility that only one of those neighbors will actually provide an instruction. If you get 2 at the same time, you're dead. At load time, at the time we are loading this program into memory, we're executing those green words after init. Up is the address of the up port. It is stored in the register A. Down is the address of the down port, and it's stored in the register B. And then we jump to go. So this is how you can initialize a computer without actually having to execute code from its RAM. And I'll show you some more examples. It's very nice to be able to tell your neighbor to do something for you. For instance, there's a hierarchy of memory available on these computers. You can get at the data on your return stack instantly. You can get at the data on your data stack instantly. You get data from your return stack with one instruction, pop, 1.5 nanoseconds. You can read data from your RAM, but it takes you 5 nanoseconds to do that. You can read data from your neighbor's RAM. If you have written a little program and then send it to him, he can give you sequential data from RAM without you having to give him explicit addresses. Or if you're doing an FFT, he can give you scrambled data from his RAM. Knowing what you're going to do with it, you can have smart memory. If your neighbor doesn't have enough memory, he can ask his neighbor. I've had as many as 10 computers chained up, passing data to me, and I can get the data as fast as I can handle it. You can actually use your neighbor's stack. These stacks are circular. You've got the 2 registers on top of the data stack, and then 8 circular registers beneath them. So if you push things onto the stack, eventually they fall off the end. If you pop things from the stack, after the first 2, you're going to get the next 8 circularly. You can circulate the stack indefinitely, which is useful, and I'll show an example. You can do the same with your neighbor. Your neighbor can give you things off his stack indefinitely. And you've got 4 neighbors. So we have lots of memory available to you in these small chunks of 64 words. 64 words is 9,000 words of memory on chip. Those are words, 18-bit words. You can think of them as 18,000 9-bit bytes, if you wish. I actually use 6-bit bytes, so I can get 27,000 characters. Here's an example of some of the programming, and this has direct relevance to energy. It's 2 star is a left shift T. This is something that we do remarkably often. There's a lot of bit splitting. Plus is an add. Next is a countdown loop. If you run out of count, it falls through and the count is discarded. So here's an example. A for next loop with a call to drive in the middle, going to be done 10 times. The loop count is 1 less than the number of repetitions. it's confusing. Micronext is another kind of loop. Instead of jumping to an address, you jump to the beginning of your current instruction word. So a micronext loop can handle, can repeat 3 instructions, because micronext can be in slot 3. So the instructions can be in slot 0, 1, and 2, or any combination of that. If I say 416 for micronext, I'm executing an empty loop with only the micronext instruction. I'm going to do 416 times, which is a microsecond. Another way of doing that would be to put a no-op in there. Now I have a 2-instruction loop. And I execute the no-op, and then I execute the micronext and repeat indefinitely, and I get a microsecond again. The only advantage of the second one is I can count longer than 256,000. I can count up to 1 million instruction delays. So those are basically delay loops. There's 2 problems with delay loops. 2 problems? 1 problem. They take energy. The computer is running. And micronext doesn't take as much energy as some of the other instructions, but still you want to keep that in mind. Of those 2 loops, the empty loop and the no-op loop, the first uses less energy, because micronext is executed repeatedly. In the second case, you're alternating between 2 instructions, no-op and micronext. So the instruction decode transistors are toggling. In the first case, nothing is changing in the computer except the count. So you're much better off with the first construct than the second if you're interested in energy. And having become interested in energy, that's the way I do it. I'll show you some. Fetch is 4th symbol for @ sign is 4th symbol for a fetch operator. So fetch means read, store means write, or bang means write, exclamation point. Those are particular symbols for historic reasons, and also because these words are used so frequently that they deserve a small word. Now, the communication between neighbors has a handshake involved. If I'm reading, as all the computers start out doing, I raise my read line. And my neighbors can look at that if they want. But everyone is reading. So it's the one massive collision of 144 times 4 ports. No problem. Somebody will break that symmetry by writing. When that happens, when both the read and write lines on a communication port are high, both computers say, ha, and take off and run. The data is transferred from my stack to his stack when both lines are high. There's no logic, no latches, no delays. It's sort of a blocking read. If I want to read, I just hang up, I just wait until I've got something to read. It takes no energy while I'm reading, while I'm waiting. The chip is idle. I mean, the computer is idle. No transistors are toggling. Communication is key. When you design an application, you've got to do 2 things, right? Write code for each of the computers involved, and then manage their communication. It's fun. There's all kinds of nice tricks you can play to make things work properly. Here's another example of code. This is put into block 200. The yellow line at the bottom describes how it is put into 200. This code, which is a message, if you will be sent 8 nodes left and 3 nodes down across what I call my ether interface. It is code that pre-exists in all the computers and passes messages back and forth. This is a clock. Actually, it's more than a clock. It's driving a ceramic oscillator, which is like a crystal, except it's easier to drive. The word drive is going to drive the crystal. Crystal is attached between a pin, which this computer has access to, and ground. I hit it with a positive voltage, and the pin will rise. I hit it with a negative voltage, and the pin will drop. I do that 10 times, and the crystal sees those drive signals and starts oscillating. So I can start the crystal running. I'll show you how I do that in a minute. Then, having started it, I don't have to delay any longer. The drive signal was a micronext loop, and it was pre-programmed to have the right frequency so that the crystal would start to oscillate. But that drive is running the computer, and it's using energy. Actually, you use energy when you put an output on the pin, and that energy probably dominates everything else. But anyway, we go to pump, and I no longer have to have a delay loop. I can read the pin, and this is a blocking read. And when the pin transitions from low to high, I wake up and do something. One of the things I do is change the polarity of the edge I'm interested in. So next time when the pin goes from high to low, I wake up. Otherwise, I'm asleep. So it takes no energy to keep this crystal running. I just wake up and kick it and go back to sleep. Ring avoids the kicking. I can pump it, and then I can let it ring for a few times while the amplitude gradually decreases, and I can pump it again. A strategy for driving a crystal with using minimum energy. And it works beautifully. Now, in the case of initializing, when I load this code, I'm initializing the state of the computer. And in this case, I have all these dupes and overs. I'm filling the data stack with numbers and taking advantage of the fact that it is circular. So in drive, when I do a store B, I'm storing something into the address in register B, and that address is the address of the pin. And the thing I am storing is already on the stack and will remain on the stack indefinitely. So I don't have to fetch a literal, which makes the code smaller. Actually, it doesn't matter because the code is only 16 words long, but still, you like to do it nicely. And you like to explore the limits of how nice is possible. So I put these numbers on the stack in exactly the right way, and then I can reference them in the code without any cost. This is a good crystal driver for several reasons. One, it only uses one pin, and pins are a limited resource. We have 88 pins on this chip. It is not as efficient as one of these little surface mount crystal oscillators. We're a very low power computer, but we're not as low power as a custom ASIC. We're better than an FPGA, much better than an FPGA. But if you design transistors unique to a particular application, we can't compete. We've got versatility. We can program all kinds of things. But for a dedicated application, you're better off with custom silicon. All right. Optimum programming. This is not anything that you aren't familiar with. The key, absolute elephant in the room, minimize the number of instructions you execute. That's almost synonymous with minimize the size of your source code. Actually, most of the instructions you execute are going to be in a loop. So you minimize the size of your loop. You can do that by factoring your application very carefully, by unrolling loops, by doing all of the tricks to minimize the number of instructions you execute. Now, actually, in the case of these computers, you can only have 256 instructions, so you have to minimize the total number of instructions as well as the number that are actually inside the loops. You want to use all the slots in the word. The slots which you don't execute, or don't use, are going to be in the right-hand end of the word. They're going to contain no ops, but they are going to be executed. They're going to take energy and they're going to take time, so you want to avoid that. It is hard and perhaps impossible to use all your slots. That's just the cost of doing business. Also, when you're trying to minimize energy, you want to recognize that there's a floor on that. You can reduce the amount of energy you use, but eventually you're going to hit the point where there's a certain amount of work to be done, a certain number of transistors to switch. You're just going to have to swallow that cost. The goal is not, you can't reduce it, except the last line. All you can do is minimize waste. Use all the slots. Fetches and stores are best put early in the word, in slots 0 or 1, instead of late in the word. Because as soon as you stop using the address bus, instruction prefetch can take place and fetching the next instruction word so it's ready for you when you finish the current instruction word. So there's a left bias to those I/O operations. Then it matters where you put the code in memory. A jump in slot 2 only has 3 address bits, which means it can jump within a little 8-word page. You want to position your jumps where they matter so that you can use a slot 2 jump. And that just means moving things around in memory. It means you need to be aware of where your jumps are and what slot they're in, and the compiler tells you that. But the best thing you can do, and actually the thing that is the most fun, is you come up with a better algorithm. Whatever you think you're doing, think about it and say, do I really have to do it this way? Is there a different way which might be better? Better in matching the constraints that the little computer puts upon you. That's to make it fast. To make it compact and fit in 256 instructions, the same rules apply, really. You want to minimize the number of instructions. You want to avoid literals. A literal is a fetch from the address in the P register, which is pointing to the next instruction in your next word in your instruction stream. And you can store a literal there. When you fetch it, the P register is incremented over the literal, and you've just picked up something in line. And when you put a number in your source code, that's what happens. That's certainly cheaper than making an explicit reference to RAM, but it's not as cheap as having something already on the stack, which is why I preload the stack with up to 8 numbers that I'm going to cycle through. Dup OR will give you a 0. Duplicate the thing on top of the stack, exclusive OR it with itself, and you get back a 0. That's a lot cheaper than fetching a literal 0, which would require 1 slot for the fetch instruction and 4 slots for the literal in itself. But this only works with 0. It works a little bit with -1, but most literals you can't construct. You have to actually pick them up. Dupe OR destroys the top of the stack. If you care about the top of the stack, then you have to have a dupe OR, but it's still cheaper. Micronext is better than next if you can use it. A micronext is often used with shift instructions. If you want to shift left 10 places, you can set up a 4-next micronext loop. It'll count down 4 places and do a shift. This is slower than actually having 10, unrolling that loop and putting 10 2-stars in line. But until you get up to 8 or so shifts, it's cheaper to put them in line. Initialize from the port. But again, the better algorithm is the better way of making your code small. Hey, timing is working out nicely. Here's another page of code. This is, I call a block. And I found that this is the amount of source code that you can fit in 256 instructions. This is an impressive little piece of code. It goes into node 8. It's reading SRAM, or it's accessing SRAM. You've got these words, read, write, and read, modify, write, which lets you address either randomly or sequentially into off-chip RAM. Off-chip RAM is absolutely essential. It's the only way we can get a decent amount of memory. We've got 1 million words of off-chip RAM in this particular RAM chip, and can address it in 50 nanoseconds. There are 3 nodes involved in reading RAM. One node has the address bus, one node has the data bus, and one node has the control lines. It's worth talking about, but I don't have time. Now, for low energy programs, first thing you have to do is be able to measure the energy. You do that with a microammeter attached to the input trace to your chip. Such meters cost a couple $1,000s, but they're absolutely worth the investment. And they let you measure the things which I'm trying to optimize. What you want is a low duty cycle. You want your computers to be sleeping. When they're sleeping, they're not doing any energy. If they're spinning, they're draining energy. A 32 kilohertz crystal will give you timing, real clock timing, without using any energy, because you're only waking up every, whatever it is, 16, 30 milliseconds to do something. If you zero your stacks, you avoid stack trashing. Whenever you read something and put it on the stack, you're pushing the stack. If the stack contains all zeros, you're pushing 0 into what was previously a 0, and it's not taking very much energy. If your stack is random, you're going to be using measurably more energy than if it's empty. Same with the return stack. And there's another thing which we only recently discovered. It matters where you put your loops. If your loop has a lot of address bits changing, it's going to cost you more energy than if it doesn't. So if you're jumping within a page, you're better off than if you're jumping way back when more address bits change. And so it goes. They're fun to program. They're challenging to program. You have to factor in forth, and this chip you have to factor into these tiny computers. And I didn't talk about wires. I showed you the code for wires. You fetch from one port, write to another port, and you've programmed the node to be nothing but a wire. It just passes messages through itself. You've got to do that. You are free to choose, put your active computers anywhere. You want to put them near I/O pins, because if you aren't reading input and writing output, you aren't doing anything. And a layout. You've got to lay out the code in a way that minimizes the amount of wire nodes you have to pass messages through. And that's what I have to say.